fine touches which I was talking about in the last few let's say the last few sentences of the last video, this is it. This is the video which will deal with the fine touches to the rough model. The fine touches applied to the rough model, I end up getting Bohr's model. Now Bohr's idea about atom was purely awesome. So he came up with bold postulates without any proof. That's how he like to put it up. That is, these are my ideas, accept it and understand the nature based on my ideas without any proof. So few of these postulates were too offensive, too radical, but still it stood tall and proved any observation associated with the atom. According to his theory, it all stand connected. According to his theory, and that we got through the observation via different experiments. So what was his theory? What were his postulates? What were his predictions? Let's find out. Now let's study about Bohr's theory. That is the model of atom. Let's say how an atom looks like, how the atom behaves, and this idea of how how atom behaves and how atom looks like was given by Niels Bohr, the Dutch physicist. Now, the reason why Bohr's theory got a great amount of success, wide acceptance, is the fact it not only answered the question which was bugging the community, the science community for years, that how atom looks like and how are the constituents of atom are arranged inside. So these questions were answered. Other than that, questions regarding what will happen if I disturb or give us a certain stimuli to the atom, what will be the response? So if I tame an atom in a particular way, what will be its response? So that question was also answered. That is, the behavior of atom was completely known at that particular time. That is, Bohr's theory gave us those insights. That is, atom is behaving like this. We know, right now we know the character of an atom, how a particular disturbance will be handled or responded by atom. That is, if I throw light, what will happen to the atom? What will atom do? What will be the changes inside the atom? So right now we know these kind of things because of Bohr's theory. Bohr's theory is the foundation of quantum mechanics as we know it. So let's study about Bohr's theory. First postulate, the electron moves in a circular orbit around the nucleus under the influence of electrostatic force. Now, nothing new about it. I already know this from courtesy Rutherford's model. Fine. Let's move on to second postulate. Only certain orbits are stable. That is, these orbits are the orbits where the electrons, they don't radiate energy. Now, this is kind of fishy. If asked what's the reason behind it, or Niels Bohr was actually questioned, why have you given this as a postulate? That is, the orbits in the electron, that is, electron in the orbits, they do not radiate energy. Why have you considered this? He said that I don't have any specific reason. I know that the electrons are revolving or are moving about nucleus. I know this. It means the only possible explanation to this particular fact is that the laws of electrodynamics are not applied in this particular case. So the orbits are, or let's say it's the region in which the electrons, when they are moving in the orbit, they don't radiate energy. It's as simple as that. So he said this is a valid reason. That is, it's like conclusion through negation. That is, if I know this is happening, it means this is not happening. So that's how he actually arrived at the second postulate. That is, I'm not radiating energy. Electron is not radiating energy while moving in the orbit. The other facts associated with the second postulates: energy is fixed and stationary. Classical mechanics may be used to describe electrons' motion in these orbits. That's the second postulate. Third postulate: radiation is emitted or absorbed if an electron moves between energy levels. Radiation is released in the form of a photon. The frequency of the photon emitted is related to the difference of the energy of these levels. Now, what he said is each electron is in a particular orbit. Now, depending upon the stimuli given to the atom, an electron can change its energy level from one energy level to another energy level. So if an electron is moving from a higher energy level to a lower energy level, then it will release a photon. Like this. We can clearly see over here, that is, this is the electron, it's making a transition to the lower state, and while doing so, a photon is released. I know that the energy of the higher state, that is, let's say this is P, this is Q. P is the name of the orbit, so energy of the P orbit is greater than energy of the Q orbit. So when an electron is moving from a higher energy orbit to a lower energy orbit, the difference of that energy is radiated in a form of a photon with a particular frequency. The frequency is governed by the difference of the energy between those two levels. This is third postulate actually deals with the radiation of photon, or let's say the radiation of light from an atom. What's the phenomena? Why does it radiate? The reason being that an electron moves from a higher energy orbit to a lower energy orbit. Only in that case, a light or a radiation is thrown out of the atom. So, third postulate deals with that phenomena. Fourth postulate, the size of the stable orbits are determined by imposing a further quantum constraint on the angular momentum of the electrons. Again, what's the meaning of this? This fourth postulate says that the angular momentum is integral multiple of h cut. H cut means h by 2 pi. Now this is again kind of fishy. Why did he came up with this law or with this postulate? Obviously, if I am coming with my idea of how things are behaving, then I sort of take postulates, or let's say, axioms or theorems, that these are the true facts, and based on that, if you consider these facts to be true, then I will explain you different things which you want to know. So Bohr did the same thing. He stated 4 postulates, that these are my 4 facts. Except these 4 facts, these 4 facts might seem to a bit of fishy to you, that's fine, but except these 4 facts, I'm going to explain everything, every other phenomena which you want to know or discuss. Every other question you want to ask about the atom, first accept these 4 facts, then I will explain you everything. So, 4th postulate, so reading all the postulates of Bohr's theory, you might have a notion that it's weird. It's like there's a clash of common sense. That is, what's happening? This is false. This can't be true. That is, you are having these kind of feelings. So just make sure that this is what, or this is how a theory is being put forward. Accept my facts first. Accept these facts, and then I will explain you everything you want to know about it. So, what are the allowed energies? So, total energy is obviously kinetic energy plus potential energy. So, kinetic energy is this, potential energy is this, Coulomb's potential electrostatic potential energy. Now, with the help of force, equation of force, that is centripetal force is equal to Coulomb's force of attraction. With this, I got a relation between the velocity, the speed, and the radius of the orbit. Now, using this, I will get hold that the total energy is equal to minus ke square by 2r. That is, total energy of an electron moving in an orbit is having a negative energy. Again, so the velocity or the speed comes out to be nh cut by me r. So again, through substitution, we can easily find out that v square is equal to ke square divided by mer. Then again, through further substitutions and using a few of the earlier results, this is the radius of an orbit. So every orbit, so Rn denotes the radius of the nth orbit. So the radius of the nth orbit is equals to n square h cut square divided by me ke square. K, just keep this in mind that K over here is 1 by 4 pi epsilon naught, and H cut is H by 2 pi. The smallest radius when n equals to 1 is known as the Bohr radius, and is given A naught. 0.529 angstrom, that is the radius of the smallest orbit. So please keep in mind that these calculations are done for hydrogen atom. You can clearly see in the earlier slides as well, we have considered Q1, Q2 to be E, an electron and a proton. So it means right now we are dealing with hydrogen atom. All these calculations are done for hydrogen atom. Whenever you want to do a calculation of some other atom, just introduce Z over here, the atomic number of the atom. Moving on, so quantization of orbital radii leads to the quantization of energy levels. So Rn, or radius of nth orbit, equals to n square a naught, and over here En, you can literally see En also, that is, energies are fixed and they are discrete. That is, I cannot, and if you are an electron moving in an orbit, you cannot have continuous energy. For a human being, for any particle which is observable to us, it can have any energy. That's the notion which we have. Okay, you can have any energy. You can run faster. You can go to a particular height. That is, every value of energy: 1 joule, 2 joule, 3 joules, 1.1 joules, 1.7 joules, all the different values of energy. It's possible. But if you are an electron moving around with nucleus, it's not possible. You have discrete values of energy. That is, an atom cannot have, an electron cannot have a value of energy minus 17.6. As a matter of fact, that is, an electron in an hydrogen atom cannot have a value of minus 17.6 electron volt as its energy. Right? So this clearly states that you have discrete form of energy. Discrete energies are allowed. Only few values of energies are available. So whenever there is a transition, you either move from one energy directly to the other energy, right? From one orbit to another orbit. So it means the energy is also, you are moving from one energy to another energy. So in between the intermediate values of energies, which are between the consecutive energy levels or orbit, they are not possible. This is exactly depicted over here, that is Bohr's theory. So I have, starting from n equals to 1, this is the energy of minus 13.6. n equals to 2, I have minus 3.4 energy. So any value between 13.6 to 3.4, it's not at all possible. I cannot have an energy or electron claiming to have an energy of minus 10 electron volt, minus 7 electron volt, minus 12 electron volt. No, you cannot, or that is completely a wrong statement, because electron is having discrete energies. So minus 13.6 is one, minus 3.4 is the other one, and so on and so forth. So as you can see, as you move higher, the energy difference, that is, energy difference between two levels, keeps on decreasing. So at higher level, it becomes sort of continuous. It's not continuous, it sort of becomes continuous. It appears to be continuous at very high values of n. Frequency of the emitted photon. Now again, if an electron is making a transition from one orbit to another orbit, then there is a difference in energy. The difference in energy is released as a form of photon. So again, we know that the frequency of the photon which is released is EI minus EF by H. Now we will substitute the value of energy at any particular orbit. So we substituted the value of En, energy at nth orbit. We end up getting 1 by lambda is equal to this. 1 by nf square, that is some constants, multiplied by 1 by nf square minus 1 by ni square. Now, we know that through spectrum analysis that the Rydberg constant was an empirical constant which we got through simply comparing the results. Now that we have actually made a theory out of it by studying spectrum, we found out that the Rydberg constant which we got through simply comparing the data, that is a spectrum, we got a spectrum line of this frequency, we got a spectrum line of this frequency, this. So just by comparing the data, we got the value of Rydberg constant. Now Bohr came up with a theory, and according to him, Rydberg, he calculated or he predicted the value of Rydberg constant, which was too accurate. It was very accurate. So that was the greatest point of success. That is, you start a theory, throw out a few postulates, explain it to everybody. Then after you are done with explanation, that is explanation of the different postulates, you start explaining different phenomena which you observe. In this particular case, spectrum analysis, line spectra. And then use your theory for explaining different phenomena, and at the end of it, get a value, predict a value. So Bohr came up with his theory, stated 4 postulates, observed, explained everything, the radius, the velocity, the energy at the nth level, everything, and then predict the value of Rydberg constant. And through experimental data, we already have the value of Rydberg constant. Now when the theory and the experiment, they both match, I say that the theory which you gave me is almost a reality. It's actually the truth. So that is the biggest point of success for any theory, and so was it for Niels Bohr. Now here is a simple diagram which shows you the different transition taking place inside an atom. So when a light is thrown, right, incoming photon is observed by the atom. So how a photon is observed? Electron absorbs the photon, its energy increases. Now it has more energy than it's supposed to have at this particular orbit. So it makes a transition and reaches at this particular spot to a higher energy level. In case of emission, that is when the light is thrown out, photon is thrown out, electron at a particular level is having energy. It makes its way down to a lower energy level, that is orbit having less energy. The difference of it is radiated as a form of light. So this is how the light is produced, or this is the reason why you have a color of your own. The clothes look like having a specific color. If you are able to observe my shirt to be blue, it's because this is occurring continuously. Emission is taking place. I'm absorbing light and the light is emitted. So I might glow, but I'm not glowing. So mostly in normal cases, the light is reflected back, and that's what you observe. But when you are asked how you produce light, literally produce light, emission phenomena is used. This emission phenomena is the same reason, or is exactly the same reason why there is why different illuminating sources like bulb, tube light, and sun itself undergoes emission, transition. Electron from one orbit is making a transition to a lower orbit, and emission is taking place. Photon is released, and photon is energy, light. So any object which produces light, or is actually the source of the light, is undergoing this emission phenomena. Now coming back to this transition from a higher level to a lower level, so different series have been defined. So one is Lyman series, when an electron makes a transition from any higher level to the ground state, n equals to 1. In that case, the photons released in that case fall under the category of Lyman series. Then comes a Balmer series, where electrons from any higher orbits they end there, or they make a transition to the first excited state, n equals to 2. In that case, it's called Balmer. Similarly, partial is for n equals to 3. So others have also suggested that, so there is Lyman series for n equals to 1, Balmer series for n equals to 2, Paschen series for n equals to 3, there is Brackett, there is Humphrey, there is Buffon. So there are different series for different values of n.
Now let's try out a simulation based on Bohr's theory. Now the basic reason behind a simulation is to give you an in-depth analysis, or let's say visualizations, so as to help understand what exactly a particular person regarding a phenomena predicted. So it's just a visualization, that is, it will help you out in understanding the theory in a much better and a deeper sense. So let's try out a small and an easy simulation on Bohr's theory. So here I have a box which is filled with hydrogen atoms, and I have this gun. This gun is throwing out light of different wavelengths. So here I can choose the wavelength thrown over here. It can be a white, that is all the wavelength corresponding to the visible spectrum, they are thrown over here, or I can have a monochromatic light source with variable wavelength. This is the UV, this is the visible range, and this is the reddish, that is higher wavelength. Now what I will do is, I have two situations here over here. Right now this is the realistic one, that is the experiment. So I don't know what will happen if I throw light on a box full of hydrogen atom. What will happen, whether a new type of light will be thrown out, or simply the light will be deflected. I don't know anything about it, right, as far as right now is concerned. It's just I've designed an experiment, and here it goes live. So totally blank of what's going on over here. So the light is being thrown. Now I'm varying the wavelength. So what I'm doing right now is increasing the energy of the light which is falling on the hydrogen atom, that is the question mark. So I am decreasing the wavelength, which means in turn I'm increasing the energy. So I'm more towards the 100 nanometer zone. Still nothing. I might be getting something out of it, but I don't know. See, here there was a small deflection, as you can see a moment earlier. Again a small deflection over there. So these type of data, or let's say results, I end up getting it. So again, if you a small deflection. So these type of data I'm getting, but it doesn't make sense what's happening inside. So based on these results, a guy, or a scientist to be precise, ends up giving his or her own idea about what's going on inside. So let's find out what according to Bohr is actually happening around. So you can clearly see that according to Bohr, electron absorbs and is continuously in some other state. See, it will change its orbit suddenly and it's over here. So you just focus on the electron. It's absorbing and it's somewhere else. It's absorbing, or when it's going down from a higher level to a lower level, it's radiating out a photon as well. See, that photon is left out. So you will see the emitted photon as well. See the dark sparkly things, violet and in red, depending upon the wavelength they have. So it's absorbing, it's going up, then it's coming down to a lower level. See, this is what Bohr predicted. You cannot literally see the movement from one shell to another shell. It's just there. It ceases to exist over here, and then it's simply over here. And while coming down, it follows the same phenomena. That is, I'm here at one moment and I'm not there at the other moment. I'm somewhere else. So this is total in-step or discrete transition, as you can put it up. So this is what Bohr predicted, that is the electron, they need to be in specified shells. Either you are there in that shell, or you are not at all, or you are in some other shell. And that's what Bohr predicted. So this is quite a simple visualization of Bohr's theory, and how, when given a disturbance in form of light, what happens in an atom. So if I pick up some other atom, this wavelength of 94 nanometer, where the things are actually happening around, I might end up getting at some other wavelength, that is absorption, emission, absorption, emission, continuous absorption and emission.
Now Let's try out a problem based on Bohr's theory. First question, when a hydrogen atom emits a photon in going from n equals to 5 to n equals to 6, the recoil speed is almost. Now I know when an atom is going from n equals to 5 to n equals to 1, there will be a release of photon. So let's evaluate the energy of the photon which is being released. Now this is equal to minus 13.6 1 by 1 square minus 1 by 5 square. So I have 24 multiplied by 13.6 by 25 electron volt. And this is the energy of the photon that is being released. Now I need to find out the recoil speed. So what I do is, here is the step which will make the difference to the question. H by lambda is equal to 24 multiplied by 13.6 divided by 25 multiplied by c. I just took the c, speed of light, on the other hand. Now h by lambda, according to de Broglie's idea or the principle, it's momentum. That is, this is the momentum of the photon. So previously at an initial condition, there was no photon. The atom was at rest. Now the photon is ejected out. Now photon has a momentum p which is given over here. If a photon is experiencing, or it has a momentum p, and initially the total momentum of the system is 0, so it means the momentum of the atom from which the photon was released now has the same amount of momentum in opposite direction. So hence this is equal to momentum of photon is equal to momentum of atom, hydrogen atom. Now, which is in turn equal to mass of hydrogen multiplied by velocity, the recoil speed. So the recoil speed comes out to be 24 multiplied by 13.6 multiplied by 1.6 into 10 to the power minus 19, as I've just expressed 13.6 electron volts into joules because it's necessary. 25 multiplied by 3 into 10 to the power 8 multiplied by mass of hydrogen. Mass of hydrogen is mass of one single proton, so it's 1.6 into 10 to the power minus 27. So I guess these gets cancelled, 1.6, 1.6, and it comes out to be close to 4 meter per second. Right? So the correct answer is C. So when a photon makes a transition from n equals to 5 to n equals to 1, when an electron makes when an electron makes a transition from n equals to 5 to n equals to 1, a photon is ejected. Now, due to this ejection of photon, the atom recoils back with a speed of 4 meter per second. Moving on to the next question. The electron in a hydrogen atom makes a transition n1 to n2, where n1 and n2 are the principal quantum numbers of two states. Assume the Bohr model to be valid. The time period of the electron in the initial state is 8 times that in the final state. The possible value of n1 and n2 are. Now I know that the radius is proportional to radius is proportional to n square. I know that radius is proportional to n square. That is Rn is proportional to n square, and I also know that the velocity is proportional to 1 by n. So the time period is basically 2 pi r divided by v, the velocity of the electron in that particular orbit. So I can clearly see with these two, time period is proportional to n cube. Now it's given that it's 8 times that in the final state. So if it means T1 by T2 is equal to n1 cube divided by n2 cube. Now if it's given that T1 by T2, that is time period in initial state, is 8 times that in the final state, it means this is equal to 8. T1 by T2 is equal to 8. It means the N1 and N2, N1 should be equals to twice of n2. So we have to look out for the options where this is valid. So I can clearly see n1 equals to 6, n2 equals to 2, it's invalid. n1 equals to 8, n2 equals to 2, no, it's invalid, not possible options. n1 equals to 8, n2 equals to 1, again I need 2 times. n1 equals to 6, n2 equals to 3, yeah, that's valid. So correct answer is your D, that is the electron is making a transition from n1 equals to 6 to n2 equals to 3. Now the takeaway points from this particular video is how Bohr corrected the Rutherford's major drawback, which was pointed out by Maxwell's theory of electrodynamics. How he actually covered it up with a simple postulate, that is, my orbit is a stationary orbit. In these kind of special orbits, my electrons can move about, accelerating about a particular point, but they will never radiate energy. So any explanation corresponding to this particular statement fails, because that's what Bohr demanded, that is, this is my postulate, accept it or leave it. So that's how he rectified Rutherford's mistake and also came up with the full-on explanation of the phenomena line spectrum. So two things which were very important is the structure of the atom, which we got to know about it, how the electrons are distributed, included in that particular aspect, and secondly, the line spectrum, the Balmer, the Bastian, the Brackett, the Profound, these kind of series, the line series, they were properly explained and to a high level of accuracy by the Bohr's theory. So in and all, it was a major success, and it also laid ground, or let's say the foundation, for the upcoming theories. And the most famous one, which everyone knows about it, is quantum physics. So Bohr as a whole, the Bohr idea as a whole was very important, as you can see out regarding the things which this idea led to. So now let's get going and study about a very special type of light which you have heard of. Not the type of light you usually deal with, but everyone knows about it. What exactly it is, I don't know. Maybe in the next video shall I tell you.